Yep.
Awesome, thank you. All right, sorry about the mouthful of the title right there. Today, I'm from Craft Academy for Excellence in Science and Mathematics at Morehead State, and I want to talk a little bit about these anomalous X-ray pulsars and some of the things that I wanted to look for in looking at a little bit different side of what's just known right now. Um, so when you, of course, first get introduced to pulsars, one of the first things that you get introduced to is the PP dot diagram. And the PP dot diagram is awesome because it distinguishes these different populations. And one of the ones that interested me was these high energy ones in the magnetar group up at this top side, the top right side of the diagram. And those are interesting as I started looking into them. And so you only had 12 of these confirmed what are called anomalous X-ray pulsars. They are just so much different, and they shouldn't really exist due to their rotational energy characteristics not matching their flux and emission characteristics. So these anomalous X-ray pulsars were kind of an odd thing at the beginning. They really didn't have such an explanation because they just didn't match with conventional canonical radio pulsars. So the first kind of train of thought of what they were and what could cause flares and X-ray events and high energy events like gamma ray bursts. The first thing that's looked at was accretion, but none of the really studied objects had any companions and were attributing to that. So then kind of looking into it, all right, what about a fallback ejecta disk from supernova remnant and thermal cooling? What about that? How is that? How could that contribute? And that accounted for most of it, but the period derivative and the slowdown rate just didn't match for these neutron stars that were doing this. And over on the left, you can actually see one of the most studied radio emitting AXPs, J1809 minus 1943, which is also XTE 1810 minus 197, and it's a very bright, strong one relative to the others. And this is a Chandra image, this composite of the archival data, and you can almost see an ejecta disk. I'm not real sure if that's what that is completely. That was kind of just a looking at it because I knew it was studied and seeing how that was going on. So that gives us our current day understanding of kind of these have to be magnetic field decay. At least that's what really is the driving understanding of them. So those are a lot different than these high magnetic field rotation-powered pulsars. These rotation-powered pulsars don't exhibit the same characteristics, even though they have high period derivatives, high energy derivatives, and are seemingly similar. They have to have correlated events such as the same thermal cooling, the flaring, the X-ray bursts, the flux changes. So that kind of distinction is what was interesting, and I wanted to kind of see with these two sources, which fell in that category of, well, they seem to look that way, but are they? So the two I choose, 1821 and 1847 over here. Some of the characteristics are listed below there. Just some things that they appeared pretty similar to the average values for the AXPs. Here are just some figures of how they relate to the rest of the AXP and SGR population. AXPs and SGRs are essentially related. They're very much thought to be of similar nature, just how are they in their age. So period derivatives and energy derivatives, three of the most the easiest to essentially measure, appeared reasonable for these population. And then as far as looking into the sources, I had access to the Chandra archive data, as anyone does, and XMM, and wanted to just kind of look into that. So for 1847, there wasn't really a great source on XMM and no Chandra data. Source there matches with the gamma ray source listed there, and not really anything as far as the pulsars related. And then on the right is 1821. and that's a Chandra image on top. It shows clear X-ray luminosity, but it's not really as the same detail as we want. And looking into the telescope, the radio frequencies, I used the Green Bank 20-meter telescope to look and use several 60-minute observations looking for, is there anything here? Unfortunately, that telescope was not sensitive enough at 13 or 1.378 or 75 gigahertz and did not get any detection. For 1821, I even tried to do a short observing campaign of a 4-week period with observations each week, but credits kind of ran out on Skynet, and so in using PS Archive, I was not able to get rid of enough sufficient RFI to identify a good signal. So we're looking for some sort of X-ray changes whenever we're looking at these, and that's important because if we do go on to look with SWIFT or our TSE, how are we going to identify these? So really we're looking for a power law or something that indicates a change, which could be related back to the flaring nature and the high energy nature of these. As in radio, we're looking for essentially the same thing, but more through the pulse profiles. Pulse profiles give a great description of frequency evolution, and you can use them to also look into the emission of and radius of emission and where the where you're getting your radiation from.
We have about 1 more minute.
All right, cool. Thank you. So one of the future things that we want to do is certainly, and we've been trying to, is get Swift TOOs put in because of the access to Swift from my advisor. He has experience with it and is very involved with it. And so he's kind of been helping me work through that. So I definitely want to get some spectra and look into what I need to get from Swift to better this understanding to get accurate spectra. Also, it would be very beneficial to be able to get, well, find archival or get new observations of these sources in sensitive radio frequencies, because these sources, they're not as active at the, as far as detected in the ATNF catalog, as active at the 1.38 gigahertz, more at around 400 megahertz. So that would definitely be something to look into. So thank you. I appreciate everyone listening. If you'd like, you can contact me at that email or tag me on Twitter. That's all.
Okay, thanks so much, Colby. Do we have any questions? If so, please type them in the Q&A. Briefly, I'll ask what observatories beyond SWIFT would be useful for this, thinking especially of up-and-coming observatories.
Well, these sources are suspected to emit in the infrared. These sources, the 1821 and 1847, are not known, I don't believe, yet to emit in infrared or ultraviolet, but those certainly would be beneficial. So anything with really, so of course, I mean, James Webb coming up with its capabilities, but I definitely need to look into that. That would be a great opportunity to expand what instruments and what would be beneficial to getting the best quality data and results.
Okay, thanks so much.
All right, thank you.
We'll now switch to our second talk, which is from Borja Anguiano. And this is called White Dwarfs in Close Binaries, a Systematic Search for Mass Transfer Systems and Supernova 1A Progenitors. And Borja is from the University of Virginia.
Yeah, that's correct. Thank you so much. Can you see the presentation?
Yes, and let me remind our audience to type questions in the Q&A, and you can type them during the talk, and then I'll pick one at the end.
All right. Can you hear me?
Yes, perfectly.
Great. Okay. Let me first introduce the team. that is making this work possible. We have myself, we have Hannah Lewis, Kyle Corcoran, Jasmine Washington, and Steve Majewski from University of Virginia. Also working with Allende Prieto from the IIC, Carles Badenes in Pittsburgh, Kevin Stasson in Vanderbilt, and John Blood in North Carolina State University. And I also would like to acknowledge the support of the AAS Accreting International Research Grant that is helping me to carry on with this research. Okay, so let me please very briefly say what is the motivation to do this exercise. So compact binary evolution still is puzzling, and leads to a panoply of phenomena that play significant roles in diverse areas of astrophysics, like for example, cataclysmic variables, nova, Taiwanese supernova, and core collapse supernova. Here on the right, you have a chart where you have like our current understanding of how the evolution of closed binaries is happening, and there is a big debate about the channels driving supernova Taiwanese progenitors, and this is one of the motivations to carry on this exercise. So thanks to the large spectroscopy surveys like SDSS, LAMOS, the number of post-common envelope binaries has increased. Still the number is around a few thousand. And a very interesting characteristic of these surveys is that most of them, they are just a single epoch. So we cannot characterize, for example, key parameters in binaries like orbital period of separation, okay? So the idea is to use this apogee survey that it provides us a multi-epoch radial velocities to try to do a systematic and exhaustive search for these compact wide sequence binaries. Okay, so we have started a comprehensive study putting things together from the Apogee, the GALEX, and the Gaia survey, and we have started to identify our candidates. So here you have a figure that is just combining the photometric from GALEX, and also we are using the spectroscopy temperatures coming from the Apogee survey. And this is how we identify our candidates for this white dwarf main sequence catalog that we are trying to put together. So here you have like from the UV blue models where single stars, they should go in this diagram, and you start to see that you have an ultraviolet excess, talking that there is like a very likely like a hot companion in this main sequence and a few giant stars that we have in Apogee. Okay, the next step we have started to do is just try to characterize our candidates through the spectral energy distribution and trying to fit a black body models to try to identify the white dwarf, and also Kurut's flux calibrated models to try to identify also and characterize the M dwarf. So this is how we are trying to put things together. Virtual observatory tools have been very useful here because there is an easy way that you can just pull out all the photometric information available for these objects. And the really good news here is that when we started to explore our candidates carefully with that, there is actually a good number of them that we can identify clearly the contribution of the white dwarf in the ultraviolet. And because we know the distances, thanks to Gaia parallaxes, we also start to characterize important parameters like radius and masses. So this is a work in progress, but things are really, really encouraging on what we are trying to find from this exercise. So let me go very briefly to very specific results we have identified. So very interesting objects and very well known from the community has started to coming out of this exercise. One of them is Draco C1. We have a PhD candidate, Hannah Lewis, that she's doing a great exercise here. And we have 43 precise radial velocities measurements from the Apogee survey. And for the very first time, we're starting to characterize precisely all these orbital parameters that you can see here in this table. Hannah has been writing a letter, so soon will be out for the community. This is very exciting because, I mean, previous orbital periods for these systems were just based in photometry, and they were talking about 300 days period. But it seems now for the precise radial velocities, we are able to see a 3 years orbital period. And of course, we are characterizing the Rho slope overflow also. This is very interesting. So another very interesting two objects that are coming in our catalog are the symbiotic binaries in the small Magallanes clouds, all these extragalactic objects. This is a work led by Yasmin Washington. And again, we have a good number of different multi-epoch apogee radial velocities, and we started to characterize for the very first time the orbital parameters for these systems. Here you have the results on this table. And also very interesting is, and this is a work led by Kyle Corcoran, another PhD candidate in UVA, we have identified 45 previously classified white dwarf main sequences systems from the SDSS. And again, thanks to the apogee survey, we can characterize not only the M dwarf very, very well, because we have a high resolution spectra now for the M dwarf, and we can get the stellar parameters and also the individual abundances. We also have these RB multi-epoch catalogs that allow us to get the orbital parameters and eccentricity, semi-amplitude, and all this, and the masses for the white dwarf main sequences. So this is an ongoing project. We're starting. We are start to get some previous results out for the community, and this is an ongoing project. I will be very happy to take your questions. Thanks for your attention.
Thank you so much. Do we have questions for Borja? Please put them in the Q&A window, and that's different from the chat window.
I think someone did this before they knew to put it in the Q&A, but it looks like there is a question in the chat.
I believe that one is for the previous talk.
Oh, sorry. I didn't even read it. Thanks.
But thank you, though. Any questions for Borja? I have a quick question.
Sure.
How much will the full Gaia mission, once it completes, change your results as opposed to the data available so far?
Yeah, that's very interesting. Gaia is doing this very low low resolution spectra with the 3 photometric bands they have, right? And so to characterize the spectral energy distribution, that would be very useful. But also, Gaia is also going to provide the radial velocities, and they have a multi-epoch, because what they give right now, Gaia, is the median value of the radial velocities of a good number of different visits. So if eventually Gaia release also the separate RB visits, that will be extremely useful to characterize all the binaries.
Okay, thank you so much.
Thank you.
So our next talk is from Paula Scotti from the University of Washington. And her title is V386 SER, a classic case of accreting pulsating white dwarfs. And I know there were some connectivity issues going on from Paul's location, so let me work on this for a moment. Okay, I think those connectivity issues are still going on, so I am going to put up the beginning of the presentation here, which I have a copy of. I think what I'll do in the interest of time here, it seems like we lost the connection with the speaker here, is to just flip through these slides. And if you do have a question, you can still put it in the Q&A, which is different from the chat. And we'll have, hopefully the speaker will be able to answer them later. Okay, here is the summary of the talk. And again, if you have any questions, make sure to put them in the Q&A window, and hopefully Paula will be able to answer them on getting back. Okay. Our next speaker. Oh, here's one. Here, okay, there is a question up in the Q&A, so I'll keep that one up there as unanswered for now. But next we have Morgan Taylor from Arizona State University, who will be talking about perturbing DBV white dwarf core composition and its effects on pulsation frequencies. Thanks.
All right, thank you so much. Like you said, I'm Morgan from Arizona State, talking about white dwarf astroseismology. So what is the motivation for my project? Astroseismology is a tool to probe stellar interiors, and white dwarfs are a choice place to start because they're the most abundant in the stellar cemetery, they're structurally simple, and we have many observations of G-mode periods for white dwarfs. So the overarching question of my project is, how does the chemical profile of a DBV white dwarf impact G-mode periods? To start my project, we need to establish a base model to compare to. So the following slides that I'll show you are for the base model only, just to emphasize that we're consistent with the literature as well as observation. So we used the MESA stellar evolution code to evolve a 2.1 ZAMS solar mass star down to a cold white dwarf. And this figure is showing the resulting chemical profile for that evolution. We ended with a 0.56 solar mass white dwarf, which is typical for the observed white dwarfs. And I'll just point out a few things in this figure. One is that the x-axis is really accentuating the helium atmosphere. So the bulk of the star is in the first third of the plot. And then the next figure is the propagation diagram for our base model. We chose to plot this at a luminosity of 100th the luminosity of the sun because that is in the observed range. And just to walk through this plot, this blue curve is the Brunt-Väisälä frequency, the orange curve is the Lamb frequency, pressure modes propagate above the Lamb frequency curve, and gravity modes propagate below the Brunt-Väisälä curve. These gravity modes were chosen to be harmonic degree of 1 because that's also an observed property for white dwarfs. And the dashed lines are the respective G modes with their radial orders. The pink dots are the nodes where they're located within the star. And the significance of this plot is that for these G modes, we're ranging, that we have periods ranging from 150 seconds to 650 seconds, and that's well within the observed range of periods. This next plot is the period evolution, where we've used the gyre oscillation code. So this, of course, is periods on the y-axis, time on the x-axis, and we have three G modes with radial orders 1, 5, and 10. So the two things to kind of note about this plot is that as you go up in radial order, you have longer periods. And for all three of these curves, as time goes on, the periods get longer. So why is that happening? Well, if you look to the right, I have a Brunt-Väisälä kind of evolution plot. As the colors get lighter, we're going on in time. So you can see that the Brunt-Väisälä frequency, the black curve is near the beginning of the simulation, and the lightest curve is near the end. So as time goes on, our Brunt-Väisälä frequency is getting lower. And if you want to kind of look at these equations down here, the overall frequency is directly proportional to the Brent by solid frequency. So over time, if that's getting lower, that would cause the periods to get longer. So coming soon, the next steps of my project are to move the carbon-oxygen core boundary outward from the base model and compare the periods. The left figure is showing a preliminary result, just like a visual of what that'll look like. So we've taken the carbon-oxygen core and extended it by about 0.2 solar masses outward. We'll compare those periods, and then the next step is to modify the carbon-oxygen core abundances and further compare those periods. That's all I have for my talk, so I am happy to take any questions you have.
Okay, thank you so much. We have a question in the Q&A from Andrew, who asks, what causes the peaks in the BV curves of little r over big R of 0.5?
Oh, that is an excellent question. Yeah, it's noisy there, isn't it? We did a little bit of investigation, and we really just think it's accurate data, and there's probably convection going on somewhere in there that's causing all the noise. But we are investigating to see if we can make that smoother. Good question, though.
Do we have more questions for Morgan? I have a question, and you may have actually said this somewhere, but I have been looking at a lot of windows here, so I'll just ask it. Is this a 1D code? And if so, how does that change things?
Yes, that is a 1D code, and we can extend it to a 3D after that. I think just for the purpose of kind of getting the data, we're going to start with a 1D code. But yeah, I think a 3D code would probably be, that would give us more accuracy for the frequencies and periods overall.
Great, thanks. We have another question here from Bradley, who asks, G-modes are confined near the surface. What effect do you expect shifting the core to have on the G-modes?
Yeah, that's a good question, and that's mostly what we're trying to figure out. G-modes are very sensitive to the chemical structure. So if we extend the carbon-oxygen core, we're also kind of having a play on mass, really. And I guess I have to think about this. When we do that, I think our periods should get smaller. But I guess we'll find out after I get my results. Good question.
Thanks so much. Maybe we'll have our next speaker get set up here while we wait for any last questions. And next speaker can share the screen.
Thank you.
Hey, so I'm actually the next speaker, but I have a bit of a dodgy internet connection. So in case it drops out, I've actually pre-recorded my talk and Tim is going to share the screen, but I'll still be here able to answer questions, hopefully at the end if my internet decides to behave.
Okay, and thanks again, Morgan, for your talk. And we'll go on to Adele's pre-recorded talk. And I'll just bring it up here. Can everyone see the screen okay? Okay, I'll begin here. So Adele Goodwin from Monash University in Australia will talk about the earliest multi-wavelength observations from the Accreting neutron star coming into outburst.
Hello, I'm Adele Goodwin, a final year PhD student from Monash University in Melbourne, Australia. Today I'm going to present to you some exciting new observations we obtained of an accreting neutron star coming into outburst. These are the most detailed multi-wavelength observations of a low-mass X-ray binary switching on to date and have revealed some interesting things. First, I would like to acknowledge my collaborators. They have worked really hard in coordinating observations with many telescopes to get these observations. So to begin with, let me explain a little bit about what an accreting neutron star is. So basically, it's a neutron star in a binary orbit, and the neutron star, because they're in such a close orbit, accretes matter from the companion star to form an accretion disk. In transient accreting neutron stars, the neutron star will accrete at a very low rate from the companion over the course of months to years, depending on the system. And then at some point, an outburst will occur, at which time material from the disk transfers directly onto the neutron star, emitting high energy radiation in the form of X-rays. Accretion disks in low mass X-ray binaries are thin, or what are called alpha disks, and that just means they follow the alpha prescription of Shakura and Sanyev in 1973. And the alpha prescription says that there's a viscosity to the accretion disk that describes how angular momentum is transported. So the current prevalent theory for what causes outbursts in cataclysmic variables, so accreting white dwarfs, as well as low mass X-ray binaries, so accreting neutron stars and black holes, is that a thermal viscous instability occurs in the accretion disk when a critical surface density is reached. And at this critical surface density, that hydrogen gets ionized, and then heating fronts that ionize the hydrogen in the disk propagate inwards and outwards from that location, bringing the disk into a hot state and commencing an outburst. So the observations we obtained were of this actual process happening in an accreting neutron star system from when the system was in quiescence all the way up until the peak of the outburst. And we observed it with more than 7 telescopes with high sensitivity instruments. So we weren't just looking with X-ray or scan monitors, we were looking with Swift and NISA to see what happened. And this is what we saw. So we were looking at 1808, which is an accretion powered millisecond pulsar in a 2-hour orbital period, orbit with its companion star. And the companion is a low mass brown dwarf that is thought to consist of 50% helium. So this is the light curve that we saw. So we've got time in days and X-ray flux as well as optical and UV magnitude here. And the blue planes are optical, the green are UV, and the yellow and pink are the Swift and X-ray observations. So quite clearly on July 25, we observed a statistically significant increase in the optical flux, which then fluctuated over the next 10 days, at which time we were looking in X-ray and UV, but we did not get a detection. 10 days after the first sign of optical activity, we got the first UV detection, and then 2 days after that, we got the first X-ray detection. So this is a really nice observation of that staggered increase as you go up in energy of the different wavelengths. But what we did not expect to see was this 12-day delay between the optical to X-ray rise. So to put this into context, there are X-ray delays that have been inferred from X-ray observations using all-sky monitors for a couple of low-mass black hole X-ray binaries, as well as 1 neutron star X-ray binary. But all of these delays were inferred to be less than 8 days. So the fact that we observed a 12-day delay is a bit strange, especially because the disconnection rate is much smaller than the other disks that the delays have been observed for. So because the disconnection rate is so small, the viscous timescale cannot be 12 days. So this means that the underlying theory, which says that this kind of process happens on the viscous timescale of the disk, is perhaps wrong. So we think something else is happening in this disk as it is coming into outburst. It's operating on a longer timescale than the viscous timescale. So we examined the temperature of the disk during this rise to outburst using our V-I color from the optical observations. And what we found was that the disk was transitioning through that hydrogen ionization temperatures. Right from the start, when it started at about 10,000 Kelvin, it went down to 7,000 Kelvin, and then it went up all the way up to about 30,000 Kelvin. So we're asking the question, does a significant amount of helium in this disk affect things? So looking at this again, perhaps we have reached the point at which hydrogen can be ionized in the disk, but the disk is not yet hot enough to ionize the helium. So perhaps this is delaying the start of outburst, and we get kind of one heating wave propagating, not really bringing the disk into the outburst state, and then another heating wave having to propagate that is hot enough to ionize the helium and cause an outburst to begin, at which time we got the X-ray detection. And perhaps this process takes 12 days rather than operating on the viscous timescale of the disk. So here are my summary slides. I'm not going to go over them because I've run out of time, but I'm really happy to take questions now or after the session as well. You can also contact me on my email here. Thank you.
Okay. Thanks so much, Adele, for that very nice pre-recorded talk. Do we have questions for Adele? And you can put them in the Q&A window. Well, I have a question. How do you find more of these?
So that's a really good question. So there's actually, we were quite lucky to get observations of this like right during the, as the outburst rise was happening. And the reason we were able to get those observations was because this source, like specific source, goes into outbursts approximately every 4 years. And we knew it was due when we decided to propose for some monitoring time with SWIFT and get the LCO network of optical telescopes to monitor it as well. But usually these kind of accreting neutron star systems are detected by all sky monitors. So there are all sky monitors on, there's definitely one on SWIFT, so SWIFT BAT. But the problem is that you often miss all of this activity before the outburst begins because the all sky monitors are a bit less sensitive, and you'll detect the outburst kind of at the very top of the like at the peak of the outburst. So yeah, so I mean, we can only hope that they will be detected by all sky monitors, but to get these really detailed observations of the rise to the outburst, you really need to be looking at a known source, and that's something that there's a project that is led by Dave Russell at New York University, Abu Dhabi, and he works, it's called XB News, and they're really trying to catch the rise to outburst of any low mass X-ray binary.
Okay, thanks so much. We have a question, several questions in the Q&A from Bradley. Nice talk. Why would the delay be longer for ionizing helium than hydrogen? Any ideas?
Yeah, so we think that the delay is probably longer because helium requires a hotter temperature to ionize. So hydrogen will ionize at about 7,000 to 10,000 Kelvin, whereas helium will ionize at about like 12,000 to 30,000 Kelvin. So we think just because the disk needs to reach the temperature to ionize helium, and it can take a little bit longer for the disk to get to that temperature, that's why it perhaps could take longer. But again, we are kind of, this is just a little bit of conjecture on our side. This is really the discussion section of our paper. We're trying to figure out what this 12-day delay could be, because it's definitely, well, it's most likely not the viscous timescale of the disk. So if you have any ideas, we're definitely open to hearing them.
Okay, thanks. And very briefly, last question. From Daniel, are there any plans to run simulations to find the cause of the outbursts?
Yeah, so Daniel, that's a really good point, and that's something that we would love to do, but we, our group, well, I don't have time at the moment to do it because I'm in the final stages of my PhD and I'm starting a new postdoc in a couple of months. But this is why we are putting these observations out here, because there are disk instability models that exist and that could be applied to this system. So we would like to encourage people to model this system using the observations that we've obtained.
Okay. Thanks so much, Adele. Really appreciate it. Our next talk is from Georgios Vasilopoulos from Yale University, and he'll be talking about the 2019 Super Eddington outburst of J0209 located at the SMC.
Hello, I think you can hear me now.
Sounds great.
Okay, so today I will talk about the discovery of a Super Eddington outburst from a previously poorly studied B-X-ray binary in the Small Magellanic Clouds. So a few background information. B-X-ray binaries are young, highly variable binary systems where the massive star loses material from a slow equatorial wind, and the highly magnetized neutron star captures this material as it interacts with the disk, usually during periastron passage. After the neutron star captures the material, matter is deposited into the neutron star magnetic pole, forming the so-called accretion column. And the interesting thing is that every few decades, these B-X-ray binary systems, or some of them, exhibit major outbursts where they exceed the Eddington luminosity and offer ideal laboratories to study super Eddington accretion into our stellar neighborhood. So about our system, RxJ0209, it was discovered, the outburst was first reported by Maxif following a detection around December 2019. And following the discovery of the outburst, we monitored the system with NICER and Fermi GBM observations, while we also obtained new star time through a DDTTO, where it was obtained during the high luminosity stage of the outburst. And this data enable us to perform an X-ray and temporal study of the system. So the broadband X-ray spectrum can be fitted by empirical model where most of the luminosity is originating from the accretion column and can be fitted very well with a cutoff power law. While the temporal properties of the system, we basically see pulsations when we search. And for this particular system, we have discovered pulsations at around 9.3 seconds. Now, given the high effective area and timing resolution of NICER, we can follow the pulse profile evolution during the outburst. And as we can see here on this heat map of the pulse intensity versus luminosity, as the outburst evolves from luminosities between 2 and 20 times 10 to the 38 ergs per second, the pulse profile remains almost constant during all the super Eddington phase. This can be translated like it implies that there is no beaming to explain the observed super Eddington luminosity. So there is no change in any system's geometry during this super Eddington phase. Now, by the study of the spin period evolution and the X-ray luminosity during the outburst, we can derive the magnetic field of the neutron star, which is a critical parameter to explain what is happening on the system. Now, the inner disk radius of the accretion disk is characterized by a balance between magnetic and gas pressure from the gas and the magnetic field of the neutron star. And as material is transferred from the inner disk radius to the neutron star, it changes the spin of the neutron star. We have transfer of angular momentum. In our case, we can use the broadband spectra that we fitted to derive bolometric corrections and go from the observed flux in the NICER and Fermi GBM band to bolometric luminosity. And then we can use the bolometric luminosity to derive the mass accretion rate and thus calculate the torque that is applied onto the neutron star. And then we can add an additional model component to account for Doppler shifts due to the binary orbit. And we can fit this to the observed period evolution by Fermi and Neisser. And from doing that, we derived an orbital period of about 47 days with an eccentricity of 0.3. But most importantly, we found that the magnetic field of the neutron star should be around 4-5 times 10 to the 12 Gauss, which is typical for a B-X-ray binary system. And on the right, you can see the observed points of the spin evolution. You can see the component that corresponds to the orbital modulation too, and the residuals of our fit. And now we can use the estimations of the magnetic field and the luminosity of the system to test in general accretion theory models that have been applied to super Eddington accretion. So, for example, we see here a plot of the maximum allowed bolometric luminosity from an accretion column as a function of the neutron star magnetic field. And according to the model by Mustikov et al., we can see what this maximum luminosity is expected to be. It's the red line. And I have also overplotted some symbols, which are the derived values for our source RxJ0209 and some other typical super Eddington ultraluminous X-ray pulsars that have been discovered that are space systems that are further away than typical B-X-ray binary systems. And according to this, we can say that RxJ can be classified as a transient ULX pulsar in our solar neighborhood. And finally, if you are interested to learn more about the system, you can please read our paper. And if you like to learn more about ULX pulsars, you can also visit our poster this afternoon. And thank you very much.
Thank you so much, Georgios. Do we have questions in the Q&A? So please type them now. I have a question for comparing to these, the pulsar ULXs. I assume you mean the ones in the extragalactic ones. How much would those have different properties because of certain selection effects?
Yeah, that's a good question. So what's happening, we now know 7 persistent ULX pulsars that are in distances of 1 megaparsec, like they're further away than Andromeda. So most of the systems that we observe are the brightest, the more extreme. And given some of the properties and maybe some beaming effects that we expect on these systems, we don't expect to have a full understanding of the population. So what is happening with the super Eddington outbursts of B-X-ray binaries, it gives us a good transition of how we expect the systems to translate, how they expect to behave as they approach super Eddington limits. So there is a selection effect, but we try sort of to understand how these systems would behave at very higher distances and try to compare their properties.
Okay, thanks. Do we have any last questions, Georgios? We can have our next and final speaker set up here. Okay, thanks again, Georgios, for the very nice talk. Our final talk in this session is from Brent West, coming to us from the U.S. Naval Academy, who will tell us about X-ray pulsar hydrodynamics, spectra, and pulse profiles, a new self-consistent model. And just to remind you, during the talk, you can put questions in the Q&A. Thanks.
Okay, good morning. Can you guys hear me okay?
Loud and clear.
Okay, great. Good morning, everyone. I'm Commander Brent West. I work at the Naval Academy. My collaborators are Ken Wolfram, retired from Naval Research Lab, and Pete Becker from George Mason University. We'll be looking at phase average spectra and pulse profiles as applicable to Hercules X1. Very quickly, this is work that we worked on in 2017. We call it the WWB West Wolfram Becker model. We are looking at the accretion columns for X-ray pulsars where we consider gas and radiation to be interacting fluids. The accretion columns can be modeled either as fully solid, completely filled, or hollow, so we have inner and outer radii arc lengths. Dipole geometry, we've got some established boundary conditions, essentially assuming zero radiation flux into the star. And then we have fan beam radiation coming out the sidewall surfaces of the accretion column, as well as the pencil beam radiation, which is coming out the top of the column. And we can assume any particular direction for the radiation pattern from either the walls or the fan beam. Considering actual radiation and energy processes, Bremsstrahlung, cyclotron, blackbody radiation are reprocessed within the accretion column. And we are considering ionized gas, electrons, and ions interacting as well. So we've got radiation, ions, and electrons, those three, if you will, fluids. So I can tell you for a given model, what our model tells us the accretion height is approximately for Hercules X1, about 11.2 kilometers. We've got a velocity profile, sound speed profiles, radiation flux, and the two fluid model there for electrons and ions essentially are very, very close in temperature, but there is a slight difference. So we've got 5 hydrodynamic ordinary differential equations we're solving in Mathematica, and then we use COMSOL to obtain a photon distribution function. COMSOL is a numerical solving element, finite element solver to give us this photon distribution function from which we can integrate over the entire length of the accretion column to tell us what the radiation is at any particular height along the column. So you give me the height, and I can tell you what radiation, what energies are coming out at that particular height. So it's a height-dependent model. So we integrate over the entire column. We previously averaged it over 4 pi radians to get just a what we consider an average spectrum, and these results that we came up that are published in the 2017 work based upon the data points from Dalfiumi from his 1998 paper. Got black body, cyclotron, and Bremsstrahlung coming out the sides of the wall and the top as well. So that's for the phased average work. But how do we get to actual pulse profiles? So how can we modify our height dependent model, knowing the photon distribution as a function of energy at any particular height, to come up with these pulse profiles? And this is data from Felix First and his team showing 3 different observations of Hercules X1 over 1 full rotation, 3 different phases during the 35-day cycle. And so our model takes into account the GR bending as the photon is emitted from any point along the accretion column. And these 2 pictures here on the right-hand side, we just are showing one accretion column just to give you an example of what we're describing here. It's emitted from the wall, bends around the neutron star, and then heads off to the observer. Also including the energy redshift, gravity redshift, as well as aberration as the plasma is coming down in its particular inertial frame. As we do the frame transformation to the frame of the star itself, then we have some aberration that we have to take into account as well. So how do we set this up? We actually have 2 accretion columns that we set up with some geometry. We have a universal X, Y, and Z axes. The observer is along the x-axis, way off at almost infinity, but is the actual, we can plug in the actual distance of Hercules X1, which right now we're using is about 6.6 kiloparsecs. But the center of the neutron star is at the center here of the x, y, and z coordinates. And then we set up 2 accretion columns. We can establish the geometry for the accretion columns based upon 2 parameters. I can tell you the spin axis. In this case, we're using the spin axis as common for both accretion columns. And then there's some offset for the magnetic field inclinations relative to the spin axes. So trying to get as close to antipodal for the 2 accretion columns as possible, but we might have to tweak it a little bit. But there's a very wide array or very wide selection of orientations from all the literature in terms of how do we try to model these accretion columns. So we're more in line with trying to get as exactly antipodal as possible. These diagrams probably a little bit difficult to interpret. I could make a video in terms of showing the spinning of these 2 columns, but this just shows the phase at 0, 90, and 180 degrees. So the star is rotating here around the omega-1 and omega-2 axes. The omega-1 and omega-2 axes, spin axes, are actually on top of each other right here. So, and the results. So as the accretion column, as both accretion columns spin around the rotation axes, the observer is going to, based upon the dipole geometry, the emission direction and whatnot, the observer may see emission from different points along the column. And I can show you diagrams later on of what that looks like. But we have all the different contributions coming from the accretion columns, both accretion columns, whether it's the wall or the pencil beam components, and we can add those up to get a pulse profile. And then from the pulse profile, we can calculate a true phased average spectrum. So on the right-hand side shows the true phased average spectrum. The black curve there is the phased average spectrum from Felix's data. And then I've got the 3 components here that show the column wall, column pencil contributions, and then the count rate pulse profile. So these are just some preliminary estimates, but I think we're within probably the 80% ballpark, getting pretty close to understanding what contributes to the 3 main peaks there for the count rate pulse profile. There is probably some background below 50 counts per second over the full 360 degrees phase rotation that we still need to account for correctly. But we're getting pretty close. And on the right-hand side there, the red curve is the total contribution from all the observed photons. Now the cyclotron absorption imprint there, that's just an ad hoc 2-dimensional Gaussian that we're currently applying. So I think we're getting pretty close to a solution that I would be considered encouraging. And then we just need to modify the particular cyclotron absorption feature and go from there. So in summary, we do have a fully self-consistent 2-fluid model. It does depend upon the photon energy is dependent upon height and all the different parameters. We can use that hydro model now to compute the phased average spectrum, a true phased average spectrum, and produce pulse profiles that include special relativity and all the GR effects of photon bending and energy redshift. And that's all I have. Any questions?
Thanks, Brent. Any questions for Brent? Please type them in the Q&A. So.
And there is a question here I see from Georgios, why the pencil beams have much different high energy cutoff. And I'd like to answer that question, Tim, though I still have time.
Yes, definitely.
Okay, so yeah, the pencil beam contributions do have different high energy cutoffs, and what I didn't mention there is that those 2 accretion columns, one of the columns has a polar cap radius of 200 meters, and the other accretion column only had a polar cap radius of 40 meters. And so the cutoff there is really just based upon how large the pencil component is, just physically much larger, so the cutoff energy will actually be a little bit higher. So the smaller the column, it just cannot pump out as many high energy photons. And this model does allow us to estimate the magnetic field strength as well, which is one of the nice things about the model, which I didn't mention earlier.
Okay, any final questions for Brent? Okay, well, thanks again for that talk and all the fascinating GR geometry in there. Well, this concludes our session. So on behalf of the AAS and all the speakers, just want to thank you all for joining again, and have a good rest of your virtual meeting. Thank you.
Thank you.
Thank you. Bye-bye.